Discontinuity in electric field near charged surfaces. Objective: to discuss the change in electric field across charged surfaces. Electric field changes whenever it comes across a charged surface. We will derive the expression from the change in electric field across a charged surface. Consider a charged surface with surface charge density sigma at point P. Let us split electric fields below and above the surface into two components each, one parallel to the surface and the other perpendicular to the surface. Depending on the shape of the surface and the charge density near P, let us draw a very thin Gaussian pillbox of small area A that contains P, extending just barely over the edge in each direction, so that electric field is uniform throughout the surface below as well as the surface above. Let us calculate the electric flux through the surface of the box from inside to outside. Flux through the upper surface is E perpendicular above into A. This flux is getting out of the box. Flux through the lower surface is minus E perpendicular below into A. This flux is getting into the box. Flux through the sides tends to 0, as our Gaussian box is infinitesimally thin. Hence, the total outcoming electric flux through the closed surface is equal to E perpendicular above into A minus E perpendicular below into A. From Gauss's law, the total electric flux should be equal to total charge enclosed by epsilon naught. Total charge enclosed in the box is equal to the product of surface charge density sigma and surface area A. Upon solving, we get E perpendicular above minus E perpendicular below equal to sigma by epsilon naught. From this result, we can infer that the normal component of electrical field E is discontinuous by an amount sigma by epsilon naught at a boundary with surface charge density sigma. Now let us consider the parallel components of electrical field above and below the surface. Consider a thin rectangular loop as shown. We know that electrical field is a conservative field, so the work done by electrical field in taking a unit charge through a loop should always be 0. That is, closed integral of E dot dl is 0. The breadth sides contribute nothing to the integral, as the thickness tends to 0 for the loop. The sides contribute E parallel above into L minus E parallel below into L amount to the integral. Upon equating it to 0, we get E parallel above equal to E parallel below. From the result, we can infer that the tangential component of electric field does not change at a charged boundary. Let us look at an example. Surface charge density of shown surface is 10 picocoulombs per square meter. Because of some external charge distribution, electric field below the surface is known to be 2 volts per meter, making an angle 60 degrees with the normal to the surface. What is the electrical field above the surface? The normal component below the surface is 2 cos 60 degrees, that is 1 volt per meter. Horizontal component is 2 sin 60 degrees, that is 1.73 volt per meter. The normal component changes by sigma by epsilon naught, which comes out to be 1.13 volts per meter. Hence, the electric field component above the surface is 1 plus 1.13, that is 2.13 volts per meter, while the horizontal component remains the same, 1.73 volt per meter. The resultant electric field is root over 2.13 square plus 1.73 square, that is 2.74 volt per meter. And it makes an angle tan inverse of 1.73 by 2.13, which approximately comes out to be 32.26 degrees with the normal to the surface.